So let's do a recap. We did it in Gram-Schmidt, as I said, where we used the angle between the vectors. So given any two vectors, red one and blue one, A and B, if we were to find the projection of the blue one along the direction of A, and we'll call it light blue one, B hat, and that is the idea. That is what we did in Gram-Schmidt in order to get the second column. Before doing that, we have to ask ourselves, why are we spending time learning how to project? What's the idea? What does it give you? So one way of thinking about it is that a vector A is a vector, of course, but it also defines a subspace because that is a direction. All scale versions of A will be along that direction, along that line. So projecting onto a vector A is also projecting onto that subspace. So if I have a vector and I'm projecting onto the subspace, what the projection gives me is a vector in the subspace that is closest to the one that I'm projecting. Suppose I have a red vector A, and that defines a subspace that's along that line. I have a blue vector B. When I project onto A, I get some vector here, and my claim is that that is the vector in that subspace that is closest to B. So this is my B, and this B hat is the one that is closest to B. How do I define closeness? So if I look at the tip of this vector and tip of the projection, and that distance is the smallest. If I take any other vector on A, say this guy as a projection, let me call that B hat. If I did, then that distance will be more because the closest would actually be the one that is along the perpendicular direction of A. So that is something to keep in mind. You will see why that is important. So the projected vector is along A, and if for some reason we had access only to the subspace, not to the whole space as we saw here, we have R2, but suppose we had access only to that red line for some reason, for some mathematical reason, then the best we can do, the best approximation of B that we can have is B hat. That might sound a bit wishy-washy at this point, but stay with me. But let's review how we did it before we move on. So while doing Gram-Schmidt, we did it this way. We had two vectors, A and B, with an angle theta between them. And we know the dot product in terms of the cosine of the angle between them. So that is the norm of A times the norm of B times the cosine of the angle. And then we know what the cosine of the angle is. So take the dot product and divide by the norms. And if we want to know the projection, all we need to know is the length, as I show you here, the length x. And then you multiply by the direction A, and then you'll get the projection vector. So x is easy to compute using basic trigonometry. X is the adjacent side, so it's the hypotenuse times the cosine of the angle, and we know the cosine of the angle, so we'll get that. Cosine of the angle is that, and multiply by the norm of B, then the norm of B from the denominator goes away, and you get that. But we actually want the projection vector, which is a vector along the direction A with a length x. The direction of A is a unit vector along A, that will be A divided by the norm of A, and times x will give you the B hat, the vector that you're looking for, the projection vector. And that turns out to be A transpose divided by A transpose A, because I have the norm of A appearing twice in the denominator, that is norm of A squared. But keep in mind that this, when we talked about norms, we talked about P norm, and this is actually true only of Euclidean norm. A transpose A will have some product of the elements of A with itself. The first element times the first element, that is the first element square. So the square comes in. Okay. So this definition or this statement is true of Euclidean norm, and that appears with a square. Keep that in mind. So that is what I have. A norm of A times norm of A squared. So A transpose A. And in the numerator, I already have A transpose B, and then I multiply with A coming from the direction of A. So that is A transpose. That gives me a nice little form, A transpose divided by A transpose A. And that is like an operator operating on any vector B. That will give me the projection of that vector along. So we can define this as the projection operator. And that is a matrix.